Imagine a universe where the boundaries between solid particles and ethereal waves blur into an astonishing mystery. Welcome to the enigmatic world of quantum mechanics, where light dances between being a particle and a wave. Our journey begins in the early 1800s with Thomas Young, an English polymath who devised an experiment that would challenge our very understanding of reality, the double-slit experiment. In 1801, Young conducted an experiment that would leave an indelible mark on science. His aim was to show that light behaves as a wave, a revolutionary idea at the time. In the classic version of the experiment, a beam of light passes through two closely spaced slits, projecting onto a screen behind them. If light were purely a particle, we'd expect to see two distinct lines on the screen. But what appeared was a series of light and dark bands, a clear interference pattern, akin to ripples on a pond overlapping. This was the first clue that light behaves as a wave. This interference pattern confirmed that light behaves as a wave. But the plot thickens. Later experiments revealed that light also exhibits particle-like properties. Enter the concept of wave-particle duality. Light doesn't just behave as a wave or a particle, it can act as both, depending on how we observe it. In the quantum realm, the act of observation plays a crucial role. When we observe which slit a photon passes through, the interference pattern disappears. The photon behaves like a particle, but when we don't observe the slit, the wave nature emerges, and the interference pattern reappears. This phenomenon is known as the observer effect, highlighting the bizarre influence of measurement on quantum systems. Scientists extended the double-slit experiment to electrons, particles with mass. Astonishingly, even electrons produced an interference pattern when not observed, revealing their wave-like nature. Here lies the profound mystery: particles with mass, when not observed, behave like waves, creating an interference pattern. But once observed, they behave like discrete particles. This challenges our classical understanding of the physical world. The double-slit experiment has profound implications, challenging our understanding of reality. Are particles inherently waves until measured? Does the universe change based on our observation? These questions venture into the realm of philosophy, suggesting that the act of observation is integral to the nature of reality itself. Are we mere observers, or do we shape the universe by observing it? Today, the principles of wave-particle duality underpin emerging technologies like quantum computing and encryption, driving the next wave of technological revolution. Quantum computers leverage these principles to perform complex calculations at unprecedented speeds, potentially solving problems that are currently unsolvable with classical computers. Taking it a step further, scientists have performed the double-slit experiment with larger molecules, like buckyballs, made up of 60 carbon atoms. Surprisingly, even these complex structures display wave-particle duality. This suggests that quantum behavior is not limited to the microscopic world but can be observed in larger, more complex systems, pushing the boundaries of our understanding even further. The double-slit experiment remains a cornerstone of quantum mechanics, reminding us that the universe is far more mysterious than it appears. As we continue to explore, who knows what other secrets await?